So let me run the entire file. So okay, so let me run this. Maybe it was too fast. Uh, Maybe it was too fast. So let me make it pause for 0.1 of a second. And in fact, let us put the quiver also. So now you should be able to see. I'm trying to enlarge everything so that you can see it in on your screen. So now when I will run, it will show you uh, the trajectory of a particle. It will show you the trajectory of a particle as it is going through the flow. Let me in fact increase the pause by 0.2. Yeah. So look, initially the flow is facing up, the particle is going like this, and slowly the velocity is more towards the right. So initially the particle tendency is to go up, but as time progresses, the particle tends to go more and more towards the right. So this particular blue line is the path line. Okay. Let me, in fact, let me remove the pause and let me do manually. So initially the particle starts over here, the time is t equal to 0. Okay. Okay. So at the next time instant, that is t equal to 0.17, the particle is trying to go up. But look, as time increases, there is still a dominance of y velocity. There is still a dominance of y velocity. But as we go towards larger value of x, we do see that the velocity is sort of having some kind of x motion towards this, because over here the y values are quite low. In fact, over here the y value is 0. Is this clear? Why the velocity field is looking like this? The velocity field is equal to x times t in the x direction, and the velocity field is equal to y in the other direction. In fact, to be clear, let me just put in the velocity field in the title. That will, so u comma v is equal to x times t comma y. So that is the velocity field. So let me stop the program. Let me open figure 1 and let me redo the entire figure. Okay, fine. So at t equal to 0, the particle is over here. The velocity is like something like this. Now at t equal to this 0.178, so at this particular point, the value of x and y is still low, but the velocity is dominated in the y direction because the time value is so low. The velocity is marginal in the x direction. As time increases, the x velocity is increasing, but we are still at a low value of x. The initial condition is chosen at a low value of x, so the flow is still dominated in the y direction. So the particle over here, it sees a velocity which is still dominated in the y direction. As time is increasing, slowly the x velocity is also coming into the picture. So you can see that the particle has in general a tendency to go up, but it is, at the same time it is slowly trying to go towards the right. Look, the time is still 0.5 seconds. So the velocity over here will be x multiplied by 0.5. The value of x over here is something like 2.5, but the value of y over here is already something like 4. So the y velocity is still dominant. Now let's see what happens. It is still going up. still going up. Now the x velocity is now gaining more prominence in these regions. So you can see the particle is trying to go more and more towards the right, while still having, it is still having a velocity in the y direction. The velocity in the y direction is constant, not constant, but it is increasing as we go towards larger value of y's. Okay, the velocity is increasing as we go towards larger value of y's. Okay, so look, it's now gaining velocity in the y direction, as you can see from the slope of the curve, but at the same time it is now going towards higher value of xs, right? So now it is, the flow is now slowly being dominated by the x direction because the value of time has increased to 1.6, and now the flow will be, the particle will see that the, at this particular point the x velocity is quite high, so it will start to go more towards the right and less towards y. Okay, so this is the path line. So far, is it clear what has happened? We've just plotted the trajectory and we have reasoned out why the trajectory looks like what it does. Okay, any doubt in this? Any doubt in this? Suppose the x velocity were to be absent altogether. Let me do that. Let me make the x velocity 0 synthetically. That is, the x velocity is always absent. So now let us run the program. What do you expect? What do you expect? Anyone? What do you expect? If the x velocity is 0, what will the particle do?
It would move only up.
It would move up and
And it will speed up.
and the speed will keep on increasing because the velocity in the y direction is equal to y. So wherever it starts, it goes to the next y. At the next y, at a higher value of y, it will see that the velocity is higher. So at the next time instant, it will go towards a higher value of y where the velocity is even higher. So it will very quickly try to go towards higher values of y. So let us see whether that is the case. Okay. Oh, it's still taking the y. Okay, I have to change the function also. One more. Forgotten to change the function over here. I need to make a lot of modifications, but you get the point. It will keep on going towards higher values of y because it needs to return a array and all that. Okay, my bad. So anyway, let us proceed. If you have understood how the path line looks, let me remove this pause. Okay, and let me show you very quickly how successive injections of particle look like. It will be clear what I should be clear. So look, this is the point of injection, and the particle numbers 1, 2, 3, 4, 5, and so on are the various particles that have come into the domain. Let me make a pause command somewhere in the loop so it would be clear. First of all, are you able to see the screen at a good resolution? That is important because otherwise you will be not making, will not make any sense at all.
Yes, sir. Yes, sir. Yes, sir.
So this is at t equal to 0, this is the point of injection. Okay, at t equal to 0, This is the point of injection. Now, when we go to the next time step, particle 1 has moved and particle 2 has come into the domain at the same point of injection. At the next time instant, particle 1 and 2 have gone with the flow. Particle 3 has now come into the picture. Similarly, particle 1 has gone into the flow and particle 2 has also gone into the flow, 3 has also gone into the flow. And remember, it is the same flow. It is the same flow that we had shown earlier. But what is the difference? The difference between particle 1 and 2 is when particle 1 was injected into the domain, listen carefully. When particle 1 was injected into the domain, there was no x velocity into the domain. When particle 2 is injected into the domain, because time has increased, there is now a certain x velocity also. Do you understand? Along with a certain y velocity, there is also a certain x velocity. So particle 2 initial condition, it is seeing a velocity which is different from the initial condition of particle 1. The only similarity between particle 1, 2, 3 and 4 is that it is injected at the same point, but they are injected at different times. Meaning particle 1 is injected earlier than particle 2, which is injected earlier than particle 3, which is injected earlier than particle 4. Is it clear so far, whatever I've said?
Yes, sir.
So let's proceed. At the next time instant, particle 1, 2, 3, 4 have gone further into the domain. Particle 5 is just being injected. Similarly for 6, 7, 8. So it's like a continuous stream of injection of blue molecules into the domain. If you can imagine that the fluid is milk and you're injecting a blue colored dye into milk, it would look something like this, given that there is a flow in the milk like we have discussed. Okay, so 1 is merrily moving along its path, 2 is merrily moving along its path, and so on. Okay. So at this particular point, particle number 12 is just entering into the domain, while particle 1, 2, 3, 4, all these have significantly gone into the domain. So like this, all the particles have been advected. So particle 15 is just entering into the domain. Now, if you connect all the points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 all the way to this, that is like the locus of all points injected at this particular point at successive times. Is this statement now clear?
Yes, sir. Yes, sir.
And now I will show you how this streak line, that is, if you were to imagine a line joining 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, if you imagine this line, how it would be different from the path lines. So let us go to the program. Let me draw so this is the streak line. This is so okay. This trajectory was the path line for the first particle. This trajectory was the path line for the first particle. Let me draw the path line for the second particle. This is the path line for the second particle. Okay. Let me draw the path line for the fourth particle. This is the path line for the fourth particle, meaning the particle number 4 took this particular path in order to arrive at this particular point at t equal to 2.5. But this particle was not the first particle. This particle was not injected at t equal to 0. It was injected at some other point in time. It was injected after particle 3 had gone into the domain. So now is it clear the difference between path line and streak line?
Yes. Yes, sir.
Yes, sir.
Okay, good. So if you want, I can share with you the file that I used to generate. And in case you are still not convinced, I can hold on. I can do something fantastic as well. I can remove recording. Yeah. So the difference. So streamline that we have. I have to open up Zerner again. So streamline, what is the basic definition of a streamline? The streamline is the line, the curve, which is sort of parallel to all the points, all the velocity vectors at all points. That is the basic definition of a streamline. So a streamline is, are you able to see the screen in Teams?
No, sir.
Okay, wait. Yeah, okay, wait. Now?
No, sir.
Okay.
Yes, yes, sir.
So streamline is sort of the line which is tangential to all the velocity vectors. So streamline is always done at a given time instant. So freeze time. So at a given time, if you have all these vectors, these streamlines will be sort of the lines which will be tangential to all the vectors. It will be parallel to all these vectors. So to find out a streamline, you freeze the time. You have the velocity fields at this frozen time. Now you imagine a hypothetical particle in this frozen time. Then you march this particle in this frozen time. You don't evolve the time for the velocity field, but you just say that for this particular particle everything is steady. That is, you have frozen the time and you integrate, you find out the trajectory of this particle. That particle is bound to follow the velocity vectors. The particle by its very definition, so dx dt, dxp dt for the particle, dyp dt of the particle, dzp dt of the particle, so they are bound to follow the velocity vectors because these are equal to the velocity components. So the trajectory of the particle will give you one curve which will be parallel to all the vectors. Do you agree with this statement? Then you take another
Yes.
particle at the same frozen velocity field, you take another particle, you integrate it. You will find another curve which is parallel to all the vectors, velocity vectors encountered by the particle. The particle has to follow this particular curve because if this particle does not follow this curve, it means that at this point the velocity of the suppose you say hypothetically that no, the particle will follow this curve. If that is the case, then the velocity at this point would be something like this, but your claim is the velocity is something like this. And if the velocity is between the, if the angles between the velocity and the particle trajectory do not coincide, then you are not solving for this equation. Okay, the fact that you are solving for this equation automatically enforces that the particle will necessarily go along this track. Then you do the same calculation for a bunch of different initial points and you will eventually find out all the curves or a bunch of curves which are parallel to the velocity. Then you unfreeze it, you go to the next time instant. Suppose you have drawn this for that first time, t1. then you unfreeze it, go to the next time, then you again freeze it in the next time, then you again do the particle trajectory in the next time. You will get a new set of streamlines for the next time instant and so on. Okay, so that also reinforce our understanding that for a steady flow, the path line and streamline coincide. In fact, if the path line and streamline coincides, the streak line also coincides for a steady flow. Is it clear, this discussion, this small discussion? So in MATLAB, you just do streamline x, y, u, v starting point for x, start point in y. So you can choose where to initialize your starting points. You can choose your starting points to start over here, 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 and then it will draw the streamlines along those directions. But Octave, GNU Octave does not have an inbuilt function streamline, so you just have to do the particle trajectory. How do you integrate? How do you find out the trajectory? You do a time marching using a Runge-Kutta method, and the function is RK45 or it's OD45. It's not 45, it's 45. So Runge-Kutta methods you might have done in your first year, right?
No, sir.
No, sir.
Okay, you might be doing it sometime in your life, but everyone does it. It's a very efficient way of doing time marching while maintaining a high degree of accuracy. Okay. Anyway, so I'm just giving you a broad overview of what happens, how things look. No need to be worried about all this Runge-Kutta and all this. No need to, in fact, be worried about the GNU Octave and all these things also. But it's a good thing to know how to program all this. There's no harm in knowing how to do programming. Okay. Is the discussions are the discussions clear so far? Whatever you have studied so far, is it clear?
Yes.
Any
So
doubt?
now the streamline and the streak lines will be same.
Pardon me?
But when you study, you said that streak line and the path line will be same.
Yeah.
But it should be uniform or like
No, it can be non-uniform. So consider this as the point of injection. So if it's a steady flow, then the flow is always like this. Suppose the flow is always like this. Okay. So at this particular point, any particle that you inject will always go along this trajectory. Do you agree with this?
Yes.
Any particular point will move along this trajectory. Similarly, any point injected after this blue point, suppose I inject the red point, even this will move along this trajectory. This orange point will also move along this trajectory. So all the different curves have the same trajectory. That is, all these points have the same path line. They are moving along the same line, meaning they are always tangential to these vectors. So this particular path line is also the streamline. And because they will always lie along this trajectory, the locus connecting all the points will also be the same curve. The locus which joins all these particles will also be the same curve, and hence it is also the streak line. Okay.
But only when the velocity will not change with time.
Yeah, so for a steady flow, right? I'm talking about a steady flow. So it can be non-uniform. It can be non-uniform, but it has to be steady. All right.
Okay.
So now let us do one problem in which we will find out the streamline, streak line, path line. Okay, so I'll be recording this for the televised thing. So I have to mute everyone. So just ask questions after I prompt. Try not to ask any questions before any prompt. Okay. Let us consider a velocity field, an Eulerian velocity field given by x. The x velocity is u equal to x upon t plus t naught. The v velocity is v naught, and the z velocity is 0. That is, it's a two-dimensional flow where t naught and v naught are constants. A colored dye is injected. So let me just draw a schematic. So it's a two-dimensional flow, and it is said that a colored dye is injected at a point A which has a coordinate given by x naught and y naught. So the question is, find the equation of the colored line visible in the flow. At t equal to 2 t naught. Given that the dye is injected, the dye injection starts at t equal to t naught. The dye injection starts at t equal to t naught, and the dye injection goes all the way to t equal to t naught. So we must find out the equation of the colored line visible. So essentially question 1 is asking what is the equation of the streak line, and the second question is what is the locus of a single fluid particle that passes through point A at t equal to t naught. So at t equal to t naught, whatever particle is pushed at point A, we want to know what is the locus of that single point, meaning we have to find the trajectory of a single point. That is the path line for a particle injected at point A at t equal to t naught. So essentially this is to find out streak line and this is to find out path line. Okay, so let's do it. Let us write down first the trajectory equation, that is dx dt is going to be equal to u and dy dt is going to be equal to v. So now if this is true, if a particle is at a certain point, it will sample this particular velocity. So dx dt will be equal to x upon t plus t naught. But now instead of choosing t naught to be fixed, or rather let us not worry about t naught because t naught is a constant. Now when we integrate this, when we integrate all of this, so before integrating let me rearrange. So this gives dx upon x equal to dt upon t plus t naught. When we integrate this, we must integrate it from some variable time ti to a final time 2 t naught. But the particle will always go from x naught to a certain x. What this statement means is that the time of injection is Ti. I do not know what Ti is. Ti can vary smoothly from t equal to t naught to t equal to 2 t naught. So I will keep it as a parameter. But what this means is the location of injection is x naught comma y naught, and this particular final location x will depend on what Ti is. If I choose Ti to be equal to T naught, then it is the first particle injected into the domain. So if Ti is equal to T naught, then it would mean it is the first particle injected into the domain, and it would travel the farthest, or it would be residing in the domain the largest. If Ti is equal to 2 T naught, it is the last particle coming into the domain, and it would be just at the point of injection. So with this understanding, we must now integrate this particular equation. We can integrate it, so it gives ln x upon xi is equal to ln 3t naught divided by ti plus t naught. Similarly, we can integrate this particular equation, because this is equal to dy dt is equal to the y component, which is a constant. So if it is a constant, integral dy is equal to integral v naught dt, where y varies from y naught to y. Again, t will vary from some intermediate time. So ti will, so this injection time is bounded between 2 t naught and t naught, and so the integration limits will be from ti going all the way to t, and all these statements that we have discussed will remain valid. So we can integrate the y equation quite easily, and it will give us y minus y naught is equal to v naught t. So this integration should be to the final time, that is 2 t naught, because it has to go from that variable time to the final time 2 t naught. So it will be 2 t naught minus of ti. So now we have the x location and y location of the particle at a final time. So we have x and y location of the particle at t equal to 2 t naught when they were injected at x naught y naught at some variable time ti. So now if I am able to eliminate this parameter ti, I will end up with a locus of all x and y's which have been injected at this particular time at any previous time ti. So we must eliminate ti to find the locus, because ti is the parameter which decides where x and y should be, and this parameterization is very much similar to the parameterization that you have done in mathematics in class 11 and 12 to describe the equation of a circle, that is x equal to r cos theta, where theta is now the parameter, y equal to r sin theta. You can eliminate theta from the equation by squaring and adding. Similarly, we must now eliminate ti to find out the trajectories of all x and y which pass through a point x naught y naught and end up finally at a time t equal to 2 t naught in the domain. How do we do the elimination? It's simple. Y minus y naught upon v is equal to 2 t naught minus ti. This implies ti is equal to 2 t naught minus of y minus y naught upon v naught. Now we can substitute this value of Ti into this equation. This means x upon xi. So if I can take an exponential of both the sides, the ln vanishes, natural log vanishes. So we have 3 t naught upon Ti plus t naught. So Ti is this. So if we add t naught to this, we obtain 3 t naught minus y minus y naught upon v naught. And this becomes 1 upon 1 minus y minus y naught upon 3 v naught t naught. So the equation, so this should be x naught, it should not be xi. Xi I have written it as x initial, but it is actually x naught. So x upon x naught is equal to, or rather x upon x naught multiplied by 1 minus y minus y naught upon 3 v naught t naught is equal to 1 is the equation of this streak line. And the physical meaning is clear. It means that for all injection times Ti, so if this is the point of injection x naught y naught, for Ti equal to 2 t naught, so for Ti equal to t naught, the particle at the end of 2 t naught will go over here, suppose. So this is the particle which was injected at Ti equal to t naught. Say this is some particle which is injected at Ti equal to 1.1 t naught. Then this is the particle injected at Ti equal to 1.2 t naught. Then so this is Ti equal to 1.4 t naught, all the way up to this particular particle which was injected at Ti equal to 2 t naught. Then the locus joining these is sort of the curve in which Ti has been removed out of parameterization. The final points x and y are thus related by this particular expression to yield us the streamline. So the green line is the colored dye that we will observe into the domain. Now, how is this different from a path line? Let us find out the equation of the path line, and this is something which you know very well how to do. So we have u equal to x upon t plus t naught and v equal to v naught, and we want to find out the path line for a particle injected at x naught y naught, and the path line should be the particle has been injected at time t equal to t naught. We want to know the path line of this particle, how the trajectory would look. Now t naught is specified to us. T naught is no longer the parameter of elimination. Let us proceed to see what will be the parameter of elimination. So from this we have dx dt is equal to x upon t plus t naught, and dy dt is equal to v naught. So when we integrate the first equation, it is dx upon x is equal to dt upon t plus t naught. We can now integrate it going from x equal to x naught to some value of x, but now the t will go from t naught to some value of t. So let me call it tf to signify the final time. So this integration will give us ln x upon x naught is equal to ln, so let me call this as xf, so it will be xf upon x naught is equal to ln tf plus t naught upon T naught plus T naught. This implies xf upon x naught is equal to Tf plus T naught divided by 2 T naught. Similarly, we can integrate this equation and it will be integral dy is equal to integral v naught dt. Y will go from y naught to yf and t will go from t naught to tf. And this will be yf minus y naught is equal to v naught times tf minus t naught. In order to find the trajectory of the particle, I know that the trajectory of the particle is now not parameterized by the initial time, but it is parameterized by the final time. That is, whatever final time I take, I will end up with a different point on the path line. So if I take a final time tf which is quite large, I will end up with a trajectory which is quite long. If I take a tf which is not that large, I will end up on the trajectory which is somewhere over here. So suppose I take tf is equal to 2 t naught, maybe it is over here. Say I take tf equal to 1.8 t naught, it is over here. Tf equal to 1.7 t naught, it is over here. Tf equal to 1.5 t naught, it is over here, and so on. So depending on the choice of tf, I will end up with a solution for x and y which will necessarily lie on the same path line. It's all a matter of now eliminating the final time to find out the trajectory. So let us write down tf in terms of the other parameters. So tf will be equal to yf minus y naught divided by v naught plus t naught, and this particular value of tf we can substitute in this particular expression. So we have xf upon x naught. So tf plus t naught will give us yf minus y naught upon v naught plus 2 t naught upon 2 t naught, and this gets simplified to 1 plus yf minus y naught upon 2 v naught t naught divided by 1, or this divided by 1 you can simply get away with. So all the x and y, so let me write down the final solution. Xf upon x naught is equal to 1 plus yf minus y naught upon 2 v naught t naught. So all the pairs of x and y will lie on the entire curve that we have shown. If you do not want to draw the entire curve for all particular times, so when you have removed the parameter tf, you are essentially obtaining the entire curve for all possible times. To know where exactly the particle lies, you tell that okay, I want to know where the particle lies at a time equal to say 3 t naught. Then you have to revert back to the original equations which were in terms of the time. We cannot make use of this equation to pinpoint where the particle is at a given time, but rest assured the particle will lie on that same curve, and that curve is the equation of the path line. This was the equation of the streak line. All the different initial points will lie at t equal to 2 t naught on this particular green curve, because these are parameterized as per the initial time, while the path line is parameterized as per the final time. Okay, so is this clear?
Yes.
Sahil Burde. चालेल
Yeah.
क्या? Okay. Anyone who wants to ask, just clarify your doubt. Samir,
Sir, here, excuse me, sir.
yeah, tell.
Sir, here, though the explanation is like proper, but then too, in one case we are talking about many particles, and the other only a single particle. So in both the cases, we are ending with a single parameter.
Yeah.
That's quite hard to digest. Then too.
So, in order to clarify the doubt, why don't you encode this in the programming language of your choice? Okay. Just try to encode it in whatever language you are comfortable with, and then plot it. Unless you do that entire plotting, it will not be clear. Okay. So just to further clarify whatever he has asked, path line is this particular trajectory, and this particular trajectory is for a single particle. That single particle, that final time is over here, final time is over here, final time is over here. So depending on what final time you take, you will end up with a point on this given curve. Okay. While the streak line, like he has pointed out, it's the calculation is done for a single particle. Suppose this is the streak line, this is the point of injection, but now the time of injection is itself variable. So this is the end point. Suppose this is drawn at some final time t final. So this is like the particle location at t final parameterized with the initial time. So this has some initial time, say t0. Now if I were to imagine another particle, or if I were to imagine a particle injected at 1.1 times t naught, that is at some time after this, it would take some other path and end up over here. Then let me imagine another particle which is injected at t equal to 1.2 t naught. It would take some other path and end up over here. So they would end up on this particular curve. All the particles would end up on this particular curve, but the difference in each of the particles is not the final time, it is just the initial time. But you are plotting them all at one final time. Hence, it is the locus where you have parameterized the initial time. Okay?
Yes.
And
So-
if you recall that animation that I just shown, that is, if you try to connect the animation with this problem, you will recall what is going on. Okay? Were you present in the? I mean, were you aware or awake in the animation?
Yes, sir. That and but
Yeah.
then too, the number of particles are
Yeah, I understand what your point is. So it's like you have a hypothetical endpoint. So it's like you have a bunch of hypothetical endpoints. These are all a bunch of hypothetical endpoints parameterized by different initial times. Does this make sense? These are all endpoints parameterized by the initial time. So like this last point is parameterized by the initial time, where the initial time is the final time. So it has nowhere to go. Okay.
So this thing would also work if say the u velocity was like it varied with y and z also.
Yeah. Yeah, it would be the same. It has nothing to do with the nature of the velocity.
Yes, sir. Okay.
So far is it clear?
So we can merge both these cases into, like the same equation by taking initial and final time and then eliminating either of them, right?
Yeah. That is the same thing. I mean, you could have done this in one shot. You could have integrated
Hmm.
it from Ti to Tf, and
Yes,
in one case you could have eliminated Tf, and in the other case you could have set Tf to be 2T naught and
Hmm.
eliminated Ti. That is the same.
Yes.
But I did not want to create an added confusion by sort of writing everything in one go. Is it
Okay.
clear, William?
Yes, sir.
I mean, if I'm doing it in an examination, fine, I'll do it in one go, no problem.
Mhm.
And let me see if
Yes,
I
sir.
find time to
I think
show.
that is,
Yeah,
yes,
tell
sir.
me. Yeah.
I think it is easier to understand it that way. That it depends on what we are eliminating from the same equation.
Yeah, I mean, effectively, we did the same thing. We did the
Yes, sir.
same, we analyzed the same thing twice. Here
Yes,
we
sir.
did it once, and here we did it once again. So, doesn't that's not a different thing that we did. Okay,
Yes.
we did the same thing twice. Doesn't matter. We did it once over here, once over there. And all this is extremely important for flow visualization. It is exceptionally important because in flow visualization, when you put a bunch of color to visualize flows, okay, then essentially you are sort of seeing a streak line. You're not seeing how the flow looks. Okay, you're actually seeing the streak line. When you see smoke coming from an agarbatti, what that agarbatti smoke that you see is actually the streak line. Now, with all this information, can you justify how that agarbatti smoke is a streak line? So, it is a bunch of smoke particles which have originated at this point, and you are watching the entire snapshot at a given time. Okay, smoke is continuously coming out from the tip of the agarbatti, and whatever shape is formed, all these smoke particles have come out from this at successive times. Is it clear?
Yes, sir.
Now, path lines are also important. Well, not path lines, but there is something called as particle image velocimetry. Velocimetry. Suppose in the flow you have put in a bunch of small neutrally buoyant particles like this, okay? And because of the flow, the particles they go over here, over here, over here, okay? So now you have two frames of photograph. The first frame is that of the white particle. The second frame is that of the blue particle. I mean, I'm just representing two different colors to show that they're actually two different photographs. So how do you take two quick photographs? You you do something. I mean, if you have a good camera, you can take photographs with a very fast shutter speed and take two successive photographs. But typically DSLRs are limited by how fast you can take two consecutive images. So typically these two photographs are done with the help of lasers. So laser, so you imagine you have the entire room which is dark, and suddenly you shine a laser in this. So wherever the particles are, the laser, the particles will shine because of the laser. Then you switch off the laser, then you again pulse the laser. So in that time period of pulsing, the velocity has acted upon the particles and the particles have moved ever so slightly. So that shift in particle is like an indication of the velocity. So that displacement divided by the pulse of the laser. So typically the laser can pulse up to 1 femtosecond. Okay, the laser can pulse very quickly. Okay, so that is why you can have the small displacement, and small displacement divided by small time, you can get the local velocity. Okay, is it clear? So this technique is widespread. It is exceptionally popular because of ease in use, and a host of computer algorithms have been developed to find out the velocity vectors. So this is called as particle image velocimetry. It's not so easy as I've made it sound, because you don't know. So if you have like bunch of particles like this, the particles have moved. In the next frame, I have something like this. Who knows which particle is from which particle? Do I can I be sure that this yellow particle has gone to this blue particle, or this yellow particle has gone to this blue particle? So it all depends on various correlations and all that. Then it all boils down to how fast you want to pulse your laser. Okay, you cannot pulse the laser too fast, because if you pulse it too fast, you do not allow enough time for the camera sensor to pick up the points. So these are various practical issues in particle image velocimetry, but nonetheless it is extremely popular, and it is like an industrial workhorse for finding out velocity fields wherever you have optical access. Any questions you have so far? So far, any questions, guys? No?
No.
So in that case, let us take a 5-minute break.